In this presentation, I am going to explain how exactly we have made use of UVM to verify a RISC-V Core design. Alright, I am Putta Satish, Principal Engineer at Maven Silicon. Now let me walk you through the agenda. So as a part of this presentation, I am going to cover what is the RISC-V RTL architecture that we have implemented and verified using UVM based test bench. And I'm going to show you the pin diagram and the pin description of this particular RTL, and later on I will show you the verification plan and the TB architecture. And at the same time I will also try to show you some of the definitions as a part of our test bench implementation, like interface definitions and transaction class definitions. And finally I will walk you through various test cases and strategy. And finally I will show you the simulation demo as well. Alright, now let me show you the RISC-V RTL architecture that we have implemented and verified using UVM, and the RTL implementation has been done in Verilog. Now if you look at our RTL has been implemented using 3 pipeline stages, and the pipeline stage 1 is responsible for program counter value generation and fetching the instruction, and the pipeline stage 2 is responsible for decoding and fetching the operands from the instructions. So basically the instruction is of 32-bit wide, which contains various fields like opcode, operand 1 like RS1 register address, RS2 register address, or if it is I-type instruction, then the same 32-bit instruction will also contain immediate value instead of RS2 register addresses. So basically in stage 2, decoding the instruction and fetching the operands from that instruction will be done. At the same time, branch and store execution will also be done in the stage 2 itself. And in the pipeline stage 3, executing remaining instructions and writing back the results of those instructions will be done in the pipeline stage 3. Alright, now let me walk you through various stages in detail. So if you look at pipeline stage 1, as I have explained earlier, it is responsible for generating the program counter value and generating instruction address output, so that from this specific instruction address output, the processor is going to fetch the next instruction. So this is about pipeline stage 1. And the pipeline stage 2, since it is quite bigger, I am showing it in 2 parts, part 1 as well as part 2. So as I explained earlier, pipeline stage 2 is responsible for decoding the instruction and generating the various operands. So if you look at this instruction mux, it's going to fetch the 32-bit instruction and it will generate various operands like RS1 address, RS2 address and IM address output. All those signals will be generated by this particular mux, and this decoder is going to decode the instruction based on opcode, funct3 and funct7, and it generates various control signals. At the same time, we will have machine control block and CSR block in the pipeline stage 2 itself, which is going to generate the complete list of control signals for the execution of various instructions. And coming to the pipeline stage 3, it contains ALU block and write back mux. So with the help of these blocks, execution of remaining instructions and writing back will be done in the pipeline stage 3. Alright, now let me show you the pin diagram and quickly walk you through the pin description of various signals in our RTL. So our RTL contains several number of inputs and several number of outputs like this, and clock is the main signal which will synchronize the entire processor's behavior, the RISC-V processor's behavior. So executing the instructions or fetching the instructions or writing back the results or generating the outputs like DM address output and DM data output during the execution of store instruction. So everything will happen in synchronism with this clock signal. And we have some signals like EIRQ, TIRQ and SIRQ. These are the signals that are related to interrupts. And similarly, we have few set of signals like DM address output, DM data output, DM data input. So these are all the signals that are going to be used during the execution of load and store instructions. And with the help of these signals like instruction input, instruction HREADY in and IM address output, the processor is going to fetch the next instruction. So that way we have got different set of signals, and each signal has got its own significance, right? In the later slides, I am going to show you the significance of various signals. And our RISC-V processor has been implemented with the help of AHB protocol, which means fetching the instructions from the external memory or giving the data to the output during the execution of load and store instructions. Everything happens based on the AHB protocol. So that's why you can see some of the signals like H response in, H ready in for the instruction as well as for the data. Alright, now let me quickly walk you through the signals. So as I told you, this clock is the main signal which will synchronize the entire processor's behavior. And reset input, it is going to reset the entire processor and it's going to clear the contents of all the internal registers of the design. So our RISC-V processor has got various registers like program counter register, which is going to hold the instructions address that's going to be fetched next. And we have an integer file which is going to contain 32 number of general purpose registers. So with the application of reset input, which is active high asynchronous reset input, all the registers will be reset. And this data input is the signal through which this processor is going to get the data during the execution of load instruction. And AHB ready is the signal which will indicate that the slave instruction memory is ready for sampling the instruction address and start driving the instruction. So this HB ready is there for both instruction as well as data. And the next one is H response in, which is useful for interacting with data memory during the execution of load and store. So this particular signal is going to help us to indicate that the AHB slave, the data memory, is ready to drive the data to the processor during the execution of load. And H trans out is useful for indicating the kind of transfer. So whether it is a non-sequential transfer or ideal transfer. And the next one is instruction input. So the processor is going to fetch the instruction through these lines. And RC in, it contains the current value from a real-time counter. If you are connecting this processor with an external counter, then through these lines this processor is going to get the real-time counter value. And as I told you, these three are the signals that corresponds to interrupts. So EIRQ is for external interrupt, TIRQ is for timer interrupt, and SIRQ is for software interrupt. And this DM write request out is used to indicate there is a request to write the data. So during the execution of store instruction, this signal will be high, which will indicate that the processor is trying to write a data into the external memory. And IM address out, this signal will produce an output, and this output represents the address of the next instruction that's going to be fetched, right? So based on the IM address output, the external instruction memory will give the respective instruction through these instruction input lines. And during the execution of load and store, the processor has to produce DM address output. So the address output is going to be produced these lines, and during the execution of store instruction, the processor will give you the data output through these lines, DM data output lines. and when it is a store byte or store half word instruction, then this mask out will help us to understand which lane of the 32-bit data bus contains valid data. Alright. So this is how we have different set of signals. Now let me show you the verification plan and UVM test bench architecture that we have prepared. So as an initial step, what we have done, we tried to make sure that the processor has been verified with the execution of all the instructions that are supported by this particular RISC-V core. So if you look at the instruction set, our RISC-V core is capable of executing various instructions like load byte, load half word, load word, and similarly store byte, store half word, store word, and there are some commands which will do some shift operations, and there are some commands which can do arithmetic and logical operations. So that way our processor is capable of executing a different set of instructions. Altogether we have got 38 number of instructions. So as an initial step in the verification process, we try to ensure that verification of execution of all these instructions are done. So that is how we have prepared our verification plan. So based on the number of instructions that are supported by this RISC-V core, we try to segregate all of those instructions in different categories. So we try to segregate all the load related instructions at one place, similarly store related instructions at one place. So that is how we try to segregate all the instructions based on the category. So we have different categories like loads, stores, shifts, arithmetic, logical, compare, branch instructions, and jump and link instructions. So this is how we have got different set of instructions, and we try to ensure that all these instructions have been verified during the verification process using UVM based test bench. So based on this list, we have prepared the verification plan, right, which will show the list of commands that we are interested in verifying, and in order to ensure that each command has been verified completely, we have defined a normal cover point for each command. At the same time, in order to ensure that each command has been verified on all the possible register combinations, source and destination register combinations, we have defined cross cover point also. So that way for every command we have defined a normal cover point and a cross cover point, and our goal is to achieve 100% coverage for various instructions, which will be under loads category, stores category, shift, arithmetic, logical, compare, branch, jump and link. So this is how we have prepared the verification plan, which will describe the list of cover points that we are going to define in our subscriber definition. Alright. Now let me show you the test bench architecture that we have prepared. So this is our RISC-V core design, and in order to verify the RISC-V core design, we have defined a test bench with 4 different set of agents, like reset agent, which is responsible for driving and monitoring the reset related stimulus. Similarly, IRQ agent is responsible for driving and monitoring the interrupt related stimulus. An instruction agent is responsible for driving and monitoring instructions, and data agent is going to act like our AHB slave memory, which is responsible for data operations like load and store. Right. So this is how we have defined our test bench with 4 different agents, and with the help of sequencers we are going to give the stimulus to the sequencers, which are going to be within the agent, and from there drivers will get the stimulus and drive it to the design. At the same time, monitors will capture them and send it to subscriber and scoreboard. So we have defined separate subscribers for coverage analysis, and scoreboard is going to get the same stimulus. At the same time, whatever the stimulus that we are driving to the design, the same stimulus is driven to the reference model also, so that reference model will produce the expected output during the execution of load and store instructions, and that will be sent to the scoreboard At the same time, the design's outputs will also be captured by the output monitors and sent to the scoreboard, and scoreboard does the validation, right? And of course, validation is not possible from the reference model every time. Like for example, if it is an arithmetic instruction, during the execution of arithmetic instruction, our processor will not produce any output through the data output lines. The data output lines will produce the outputs only during the execution of memory instructions like load and store. But in most of the cases like arithmetic and logical instructions, instead of producing valid output, the design's internal registers, the content of those internal registers will be modified. So we have to compare the data in those destination registers with the expected values. So that is why we are using RAL components also, which can do the backdoor access and send it to the scoreboard. So validation happens with the help of the RAL backdoor access here. Alright. And in order to make sure that we are getting complete 100% coverage, we have developed test suite which is going to cover all the possible commands. Right. Now let me show you the micro-architectures of various test bench components. If you look at the micro-architectures of agents, they contain drivers, monitors and sequencers, and of course each agent is a configurable component. And if you look at the micro-architecture of reference model, it gets the stimulus from various agents, all the 4 agents, and depending upon the type of instruction, the respective block will be utilized within the reference model and it produces expected output. And that output will be captured by the output monitor and sent it to the scoreboard. And coming to the scoreboard, it gets the data from various components like data agent, instruction agent, and even from RAL components. And depending upon the type of instruction, the scoreboard will decide what kind of comparison must be done. And based on that, scoreboard will do the comparison and generates the report. Now let me show you the interface definitions. So as I have shown you earlier, this is our RISC-V top module definition, which contains several number of inputs and outputs. So since our test bench architecture is going to contain 4 different agents and each agent is going to work with a dedicated interface, altogether we need to define 4 interfaces. So now let me show you which signals will be a part of which interface. So if you look at these signals like EIRQ, TIRQ and SIRQ, these 3 signals are responsible for interrupts. So that's why they will be there within the interrupts interface. Similarly, all the remaining signals like DM address output, DM data output, mask out, request out, H trans out and data in, H ready in, H response in, all these are the signals that are going to be a part of load and store instructions. So that's why they will be a part of data interface. And similarly, reset and real-time clock, we have made them as a part of reset interface. And instruction input, H ready input and IM address output, these 3 signals are responsible for getting the instructions. So that is why they will be a part of instruction interface. Alright, let's proceed further. The next one is transaction class definition for the instruction agent. So the transaction class for the instruction agent is responsible for modeling the instructions that we are going to drive through instruction driver, right? So basically our RISC-V processor is going to accept 32-bit instructions, and of course those 32-bit instructions will contain different fields based on the instruction type. So we have different types of instructions like R type, I type, S type. So different types of instructions will contain different fields. Like if you look at R type, it contains the fields like opcode, RD, funct3, funct7, RS1, RS2. But if you look at I type, instead of having RS2 and funct7, it will have a 12-bit immediate value. So that way we have got different types of instructions with a different set of fields. So at the end of the day, our driver has to drive 32-bit instruction. But we cannot generate the complete 32-bit instruction in a single shot, right? Because the 32-bit value cannot be completely randomized. Depending upon the type of instruction, we have to decide what should be the opcode value, what should be the funct7 value, or what should be the funct3 value, right? The RISC-V ISA defines the opcode values for various instructions, funct3 values for various instructions, and similarly funct7 values for different instructions. So based on the instruction that you wanted to generate, you need to decide what are going to be the values of funct3, funct7 and opcode. So we cannot generate complete 32-bit instruction at a time. We have to generate each field separately depending upon the instruction, and finally we have to concatenate various fields and generate 32-bit instruction. That is what exactly we are going to do in our transaction class definition. So in our transaction class definition, we have defined various fields like opcode, RD, funct3 and funct7, RS1, RS2, immediate value. So everything has been declared as rand type, and we have written some constraints so that depending upon the type of instruction, opcode, funct3 and funct7 values will be decided. And finally, after randomization, within the post randomized function, based on the type of instruction, we are using concatenation operation to generate 32-bit instruction. So if it is R-type instruction, we will concatenate funct7, RS2, RS1, funct3, RD and opcode. And if it is I-type, instead of funct7 and RS2, we will concatenate IMM value, which is of 12-bit wide. So this is how we have used post randomized function to generate 32-bit instruction based on various fields and the type of instruction. Alright, now let me show you the verification strategy that we have followed and the different test cases that we have implemented to achieve 100% coverage. So one of the test case that we have implemented is reset test case, which is going to cross check how the reset scenario is working in the design, right? Whether the design is getting reset properly or not. So how did we verify this? So we have driven the reset stimulus and waited for the design to complete the reset operation, and after that we tried to read the content of all the design's internal registers like program counters and all the 32 general purpose registers and compare them with 0, because 0 is the default value of all these registers upon the application of reset input. So this is our verification strategy during the reset test case simulation. And similarly, when you look at R-type test case, so this R-type test case is responsible for generating various R-type commands like add, subtract, right? So how did we verify? What is our verification strategy in this? We have written the data into source registers using the backdoor write access, and after that we have driven the commands like add, subtract, and after the execution of those commands we try to read the data from the destination registers and compared with the expected data. So this is our verification strategy in case of R-type, and even the same verification strategy has been followed even in the I-type logical test case. During this simulation, we tried running simulation with different seed values, and we tried to identify an efficient seed which is going to give us a better coverage with a lesser number of instructions, right? So that way, for every test case we try to identify the best possible seed numbers which will give us the good coverage with the help of lesser number of transactions. So we have R-type test case which is responsible for covering R-type commands, and I-type logical test case which is responsible for generating and driving I-type logical commands like XOR immediate, OR immediate, AND immediate and shift immediates, right? Similarly, we have few more test cases like U-type test case which is responsible for generating U-type commands, and BEQ test case which is responsible for generating BUQ command, and BGE type of test case which is responsible for generating BGE commands like BGE and BGEU. So that way we have identified the best possible seed numbers for every test case. Alright. Similarly, we have few more test cases like BLT type test case, I-type load test case, I-type load half word test cases, and similarly store command test case which is responsible for generating all the store commands, and JAL test case, JALR test case. So that way we have defined multiple test cases so that all these test cases will together generate all the possible commands, and we are going to achieve 100% coverage with these many number of test cases. Alright, now let me show you the simulation process. Let me show you the demo of it and how exactly we have achieved 100% coverage. Alright, now this is my current directory which contains various folders. So basically all these folders are going to contain the source codes of RTL as well as our test bench components, right? So interface is the folder which contains interface definitions, RTL folder contains RTL definitions, TB folder contains the TB components definitions like drivers, monitors, agents, and the TB architecture, that is environment, and test case folder contains the test library, and vplan and ucdb files, this folder contains the verification plan, and sim is the directory where I am going to run the simulations. Now let me quickly open the verification plan. So this is my Excel sheet which contains verification plan. So let me quickly open it. So this is my verification plan. So as I have shown you earlier, we have defined verification plan with various set of categories in the instructions, and under each category we have multiple commands, and for each command, to ensure that every command has been verified, we have defined a normal cover point and a cross cover point. And basically this cross cover point is to ensure that all these instructions are working with all the possible register combinations, right? And our goal is to achieve 100% coverage. As of now, if you see, the coverage column is not containing the coverage because I have not run simulations as of now. Okay, now let me run the simulation, and once the simulation is run, it's going to generate the coverage report, and after that I will annotate that particular coverage back to this vplan so that we can compare what is our goal and what is the coverage that we have achieved. All right, now let me show you the simulation process. Now, so as I have shown you earlier, sim is the directory where I am going to run the simulations, which will contain the makefile script for running the simulations. So as of now, if you look at the sim directory, apart from makefile, nothing else is there. It was very clean. So let me run the simulation in the regression mode so that all the test cases that I have shown earlier will be running one after the other, and each test case is going to generate separate coverage report. And finally, after completion of running the simulation with all the test cases, this regress target will also do merging so that all the coverage reports will be merged and it will generate a single merged coverage report, right? So let me start running the simulation, which will take certain time. And for each test case, the simulator is going to generate a separate log file so that we can analyze those log files later and understand if there is any failure in any test case. If the test case is passed, right, so this kind of display will be printed. This is how we have implemented our TB source code, right? And if it is failed, it will display the similar message as fail. At the same time, if the test case is not passed, if there is any mismatch in the scoreboard during the comparison, if there is any mismatch, we try to print that comparison mismatch message using UVM error macro, so that after running the simulation, if there is any mismatch, the log file will show how many number of UVM errors are there, so that we can understand if there are any mismatches. So finally the simulation run is completed, and after that it is merging various coverage reports and generating a merged coverage report, right? And the name of that coverage report is RISC-V coverage of regress.ucdb. So let's try to annotate this particular coverage database to our V plan. So this is the coverage that we have derived finally after merging process, so that you can see the coverage that we have achieved that's being filled in this particular column, so that you can compare what is our aim and what is the coverage that we have achieved, right? So we have almost achieved 100% coverage for almost all the commands. All right, so this is how we have verified the RISC-V core design and made sure that all the instructions are working fine. And as a part of next implementation, we have even written few more test cases so that we have verified the execution of assembly programs also, so that instead of each instruction, a set of instructions which are going to be executed in a sequential manner, we have implemented few test cases for verifying assembly programs as well. All right, that's all from my side. Thank you everyone.